Watch a cruise ship come into port sometime. Not from the dock, from somewhere with a real vantage point. Ideally above the waterline where you can see the full scale of the thing. A ship the size of a 20-story building, carrying 5,000 people and enough food to supply a small town, gliding silently toward a berth. No churning water at the stern, no visible struggle. And then, almost impossibly, it turns. Sideways. The whole structure. 200,000 tons of steel, balconies, swimming pools, and buffet restaurants rotates and slides into the berth like someone parking a car in a garage. No tugboats, no drama. The passengers on the upper decks are sipping coffee. None of them know what just happened beneath them. Most people, if they think about it at all, assume a cruise ship works something like a very large car. Big engine, shaft, propeller. Water pushed backward, ship moves forward. The engine turns faster, the ship goes faster. Simple enough. That mental model is intuitive, and it has one significant problem. It hasn't been accurate for a major cruise ship in decades. The actual system underneath a modern cruise ship has almost nothing in common with that picture. There is no direct connection between the engines and the propellers. The engines don't touch the propellers at all. What they do instead is something far stranger and far more interesting. They generate electricity, massive amounts of it, and that electricity is what actually moves the ship, routed through a power distribution system that runs throughout the entire vessel, driving motors that sit not inside the hull, but outside it, hanging beneath the ship in sealed pods that rotate freely in any direction. The thing, doing the actual pushing, is underwater, invisible, and spinning on an axis that can point wherever the system tells it to. A large cruise ship needs somewhere between 10 and 100 megawatts of power at sea. The lower end of that range is enough electricity to supply a mid-sized town. The upper end covers a small city. Every watt of it is generated on board from scratch, continuously, for the entire length of the voyage. There is no grid connection. There is no shore supply at sea. The ship is not a vehicle with a hotel attached. It is a power plant with a vacation attached. To understand why it works this way, you have to go back to the older system and understand why it failed. Traditional marine propulsion was mechanically logical. A diesel engine produced power at the crankshaft. A gearbox matched the engine's rotation to the propeller's required speed. A long shaft, sometimes stretching 50 or 60 feet through the lower hull, connected the gearbox to the propeller. At the stern, a separate rudder handled steering. Move the rudder, deflect the water flow, change direction. The system worked. It moved ships across oceans for generations, but it carried a set of constraints that, on a vessel designed to carry thousands of paying passengers, become deeply expensive problems. The shaft problem was the most fundamental. Long, rotating shafts vibrate. Under heavy load, the vibration transmits directly into the hull, into the structure, and into every cabin bolted to that structure. On a cargo ship, vibration is an inconvenience. On a cruise ship full of passengers who paid thousands of dollars for a relaxing experience, vibration is a product failure. The traditional answer was engineering isolation. Rubber mounts, damping systems, structural absorption. It helped, it never fully solved it. The rudder problem was the second constraint. A rudder only works if water is flowing across its surface. Water flows across its surface when the ship is moving. When the ship is docking, moving at near zero speed, trying to place itself with precision into a specific berth, the rudder becomes nearly useless. The conventional answer was bow thrusters, small propellers mounted in transverse tunnels through the hull near the bow, pushing the front of the ship sideways. They helped too, but thrusters are limited in power, and a very large ship is a very large problem to solve with a few small thrusters. The third constraint was spatial. Shafts, gearboxes, and rudder systems occupy significant volume in the lower hull. On a passenger ship, the lower hull is prime real estate. Every cubic meter consumed by mechanical drive infrastructure is a cubic meter that cannot be a cabin, a water system, a fuel tank, or a mechanical room serving passengers rather than propellers. The geometry of traditional drive systems was eating into the vessel's revenue-generating capacity. The fourth constraint was subtler but equally important. A ship's power demand is not constant. At sea and underway, propulsion consumes most of the load. In port, propulsion stops, but everything else keeps running. The air conditioning, the refrigerated food storage, the freshwater production, the lighting, the entertainment systems, the laundry, the internet. This is called the hotel load, and it is enormous. A traditional mechanical drive system is optimized for one thing: turning a propeller. It has no elegant way to share energy between propulsion and everything else. The engine either drives the shaft or it doesn't. The result is a system that is efficient at exactly one task and poorly suited to the complex, shifting energy demands of a vessel that is also, simultaneously, a full-service hotel. The engineers solving this problem were not primarily asking how to make the ship go faster. They were asking something larger. How do you build a power system that serves the entire ship, not just the propeller? The answer was to get rid of the mechanical connection between the engine and the propeller entirely. Turn the engine into a generator. Feed the power into a central electrical system. Distribute it wherever the ship needs it, in whatever proportion, at any given moment. The diesel-electric system was not a propulsion upgrade. It was a complete rethinking of how a ship manages energy. Here is how it actually works on a modern vessel. Below decks, the ship runs 4, 5, or 6 large diesel generator sets. Each one produces between 9 and 15 megawatts of electrical power. They are not driving anything mechanically. They are feeding electricity into the ship's main high-voltage switchboard, typically running at 6,600 to 11,000 volts. From that central distribution point, power routes throughout the vessel. Some goes to the HVAC systems, the chillers that keep 5,000 passengers comfortable regardless of whether the ship is crossing the Caribbean or the North Atlantic. Some goes to the desalination plants that produce the ship's fresh water from seawater. Some powers the galleys, the refrigeration, the laundry, the medical facilities, the navigation systems. And some, the majority when the ship is underway, routes to the propulsion motors. Norwegian Bliss carries 2 propulsion motors rated at 22,000 kilowatts each. That is 44 megawatts of electrical power being consumed just for propulsion on a single ship, continuously while at sea. The scale of the generating infrastructure required to supply that is not what most people picture when they imagine a ship's engine room. This is not an engine room in any conventional sense. It is an industrial power station that happens to be inside a floating building. Now comes the part that actually changes everything. Instead of routing that electricity to motors connected to fixed shaft lines, modern ships send it through cables to motors mounted outside the hull entirely. The motor sits in a sealed, streamlined pod, roughly torpedo-shaped, suspended beneath the ship's stern. The propeller is attached directly to the motor shaft. The pod is mounted on a bearing that allows it to rotate 360 degrees around its vertical axis. There is no shaft running through the hull. There is no gearbox. There is no rudder. The pod is the propeller, the gearbox, the shaft, and the rudder simultaneously, collapsed into a single unit hanging below the waterline. These systems are most widely known by the name Azipod, a trademark of the Finnish engineering company ABB that pioneered the technology, though the broader category is called podded propulsion. The implications cascade outward from that one design decision. No mechanical vibration path between the motor and the hull means the motors are effectively acoustically isolated from the passenger spaces. The silence in the cabin, the absence of engine vibration that plagued older ships, is not a luxury feature bolted on by the interior designers. It is the direct mechanical consequence of removing the physical connection between the drive system and the structure. The quietness is the engineering. No rudder means steering happens differently. The pod rotates. When the bridge requests a course change, the pods angle toward the new heading and generate thrust in the required direction. When the ship needs to move sideways, into a berth for example, the pods rotate to 90 degrees relative to the hull and push the entire vessel laterally. When the ship needs to stop quickly, the pods can reverse thrust without changing the physical orientation of the vessel. The control system is essentially vector thrust, the same principle that makes modern fighter jets so maneuverable, but on a ship. That scene at the beginning of the cruise ship turning sideways into its berth is precisely this. The bridge crew sets a heading vector. The pods rotate to the required angle. The ship moves laterally under its own power with precision. Some ports still require tugs by local regulation or convention, and large ships in tight harbors sometimes use them for safety margin. But the capability to dock without them is real, and it fundamentally changed what port operations look like for modern cruise vessels. The ship doesn't stop being a power plant once it reaches the dock. When a cruise ship ties up for the day, the propulsion motors go idle. The generators do not. The 5,000 people on board still need cooling air, refrigerated food, hot showers, internet access, and lights. The water-making plants still need to run. The medical bay, the laundry, the kitchens, all of it continues. A large cruise ship at berth can consume fuel at a rate that sounds to most people like a mistake. Up to 250 tons per day on the largest vessels. Roughly 80,000 gallons. The ship is not wasting that energy. It is running a city while parked. And here is another layer that almost nobody thinks about. The fuel isn't just fuel. As the tanks drain over the course of a voyage, the distribution of weight across the hull changes. Fuel tanks are not just energy storage. They function as ballast. Naval architects have to account for how the ship's trim and stability evolve as fuel is consumed, redistributed, or transferred between tanks. Fuel consumption is a stability variable as much as an operational cost. The voyage is, in part, a managed exercise in shifting the center of gravity of a floating structure across several days at sea. Pull back far enough and the full picture becomes clear. The efficiency gains compound over time. Compared to conventional propulsion, potted drive systems reduce fuel consumption by up to 20% on comparable vessels. A BB's documentation covers more than 1 million tons of fuel saved across the fleet over 3 decades. 1 million tons from a single architectural decision. Put the motor outside the hull and let it rotate. The savings are not marginal, they are structural and they are permanent. The architecture that makes this possible also makes the next generation of ships technically natural. The same diesel-electric system that freed propulsion from the engine room now makes LNG-powered cruise ships straightforward to build. The power grid is the same, the pods are the same, the fuel source simply changes. Hydrogen fuel cells, when the technology matures at scale, plug into the same distribution logic. The propulsion revolution already happened. What is still evolving is where the electricity comes from. Go back to the ship at the berth. The early morning light. The passengers on their balconies, coffee in hand, watching the water. Nothing visible is happening beneath them. No sound, no smoke, no tug standing by. Just a 200,000-ton structure holding its position against the tide, adjusting slightly as the generators run, as the pods hold their angle, as the power grid distributes load across systems the passengers will never see. Somewhere below the waterline, sealed in a pod that most people on that ship couldn't locate on a diagram, an electric motor is doing exactly what the software tells it to do. Holding still, waiting, ready to rotate in any direction at a moment's notice, pushing that entire structure wherever the bridge requires. A cruise ship looks like a floating hotel. It is actually a floating power plant that decided to take people on vacation. The engineering underneath it is invisible by design. The invisibility is not accidental. When the system is working, you don't see it, you don't hear it, you don't feel it. You just stand on the balcony, sip your coffee, and watch the water, with no idea at all what is holding you there.